contractors, and reality capture professionals transform point cloud data into accurate, construction-ready BIM models and digital deliveries. Through our Scan-to-BIM services, we support projects across commercial buildings, industrial facilities, healthcare, education, infrastructure, and complex renovation environments, helping teams make confident decisions from existing conditions through design and construction. Before we begin, I'd like to cover a few housekeeping items. Today's session is being recorded, and the recording will be shared with all registered attendees after the webinar. We encourage you to submit your questions through the presentation using the Q&A feature. We'll reserve the time at the end of today's session to address as many questions as possible. If we are unable to answer your question live, we'll ensure it reaches our speaker afterwards. Reality capture has become one of the most important foundations of modern design and construction. Yet one of the biggest challenges project teams continue to face isn't simply collecting data, it's choosing the right method before stepping onto the job site. Every project presents a different balance between speed, accuracy, site complexity, safety, budget, and schedule. Selecting the wrong capture approach can result in unnecessary field visits, costly rework, missed deadlines, and data that simply isn't fit for purpose. The question isn't whether laser scanning or mobile mapping is better. The real question is, how do you choose the right reality capture workflow that delivers the accuracy your project needs without sacrificing efficiency? That's exactly what today's webinar will explore. In today's session, we'll examine the strength and limitations of traditional laser scanning and SLAM-based mobile mapping, discussing when each technology performs better, and introduce a practical framework that helps survey teams make smarter decisions before mobilizing to the field. It's now my pleasure to introduce today's speaker, Matthew Malencia. Matthew is the Senior Technical Product Manager at Exyn Technologies, where he leads the development of autonomous robotic systems from concept through commercialization. He holds a PhD in robotics from the University of Pennsylvania and brings extensive expertise in robotics, artificial intelligence, autonomy, and systems engineering. Prior to joining Exyn Technologies, Matthew led cross-functional product initiatives at Zipline, delivering a scalable FAA-compliant solutions. Today, he closely works with both technical and business teams to develop practical technologies that solve real-world challenges across construction, infrastructure, and other heavy industries. Matthew, we are delighted to have you with us today and look forward to learning from your experience in advancing autonomous reality capture and field robotics. And the stage is yours. Thank you.
Thank you so much, and welcome to everyone who's here. Yeah, as you said, I'm excited to be here and chat a bit about these technologies, reality capture, the different technologies that exist, where autonomous robots fit in, where they fit your needs, and how to think about these different technologies and when to use them, when to invest in them, where they are best leveraged. And so today, I'm going to be talking kind of in four main parts. One is a technology overview. I'll talk about some of the more traditional technologies briefly, just so everyone's on the same page. I imagine many of our attendees already know about some of this stuff since it's been around. I'll then touch on SLAM and SLAM scanners with a little more depth because it's a newer technology, and then a deeper dive into autonomy. The word autonomy gets thrown around a lot, and so I want to be very clear about what it is we're talking about when we talk about autonomy. And then we'll talk a bit about speed and accuracy, which are the main metrics or aspects that we trade off with these different technologies. Then we'll get into the decision framework, how to think about these different technologies, when they're useful, when they're best suited. And then we'll give some real world examples because I think it's really good to ground all of this kind of stuff in the real world, in applications that matter to you all. So we will start by talking a bit about the technology itself. So to start, we'll talk about terrestrial laser scanners. These emerged in the early 90s, and so I expect most people who are familiar with this space, with the surveying space, know about these. They're stationary, LiDAR-based scanners, and they require setup in multiple locations in order to cover an entire area. Depending on the complexity of that area, you have to worry about shadowing and getting many viewpoints so that you can get into every corner, every part of the full space that you're trying to survey. The example shown here is the Trimble X9. The mid-range TLS has features like automatic calibration and leveling. As with many laser scanning devices, the goal is to accurately capture reality. The examples shown here are extremely variable. There's MEP engineering, accident scene data capture, facade capture. These are just a couple examples. And since traditional TLS has been around for 30 years, it has a lot of different applications all over the place. Some of these applications overlap with some things in the SLAM scanner world. But before we get to some of that, I want to talk a bit about the underlying SLAM technology. So around the same time in the early 90s, when traditional laser scanners were reaching the market, foundational SLAM technology was being developed. SLAM stands for Simultaneous Localization and Mapping, and it is a set of computational methods that were developed in the field of robotics. They're not actually specific to one solution or one method, but rather a set of methods. But the goal for all of them in robotics was to enable a robot to know where it was, that's localization, and what's in the world around it, that's mapping. So the image on the right here shows blue circles that represent uncertainty around environmental features as well as the robot positions. And so as the robot navigates the world, observes and reobserves features, those blue circles shrink. And so that's kind of the SLAM process happening in real time, is taking that uncertainty and squashing it down into an accurate estimate of where the robot is and what's in the world around it. And this SLAM process is continuously calculating the best guess of both of those things, the map and the robot state. It's doing this so that it can safely navigate its environment. Now, it wasn't until maybe the mid-2010s that this technology was commercialized into handheld laser scanners. So what happened is folks realized that calculating an accurate position of a laser scanner device and creating an accurate map around it isn't just useful for robots navigating the world, but is really valuable for surveying. So SLAM scanners use the same underlying methodology as seen in robotics. And just like terrestrial laser scanners, it's firing laser pulses to measure the world. However, with SLAM scanners, the device itself is not tied down to a single place. SLAM methods track the movement of the device so it can be carried around, moved around, and navigate the world, whether it's held by a human, mounted on a backpack or a vehicle, or mounted on a robot and being used by that robot for navigation, safe navigation in the world. But because of this motion, SLAM scanners can accumulate errors over time, which is called drift. There are, very minute errors or uncertainty in every step of the process, but as time goes on, those errors accumulate. There are methods to reduce this drift. So for example, a lot of systems add GPS sensors to help the device know when the estimate is veering off. There's also a method called loop closure. And so that's when the sensor sees parts of the environment that is already seen before. So overlapping spaces that you've already been in, and it recognizes that it's been there, corrects those errors, and continues. And so that's kind of a fundamental limitation of all things SLAM, but there are methods to combat that drift. Now, like I said, SLAM started in the robotic space. And so one thing that SLAM scanners have enabled is robotic surveying or robotic scanning. And one of the big enablers in this space is autonomy technology. But like I said earlier, Autonomy is this word that gets thrown around and means a lot of different things to a lot of different people. So I'm going to break down for you all the different levels of autonomy and what they mean. And then when we talk later about some of these examples and technologies, you'll see kind of where that autonomy fits in to your applications, into different things that are in the market and how you might use them. So first, level 1 autonomy. I skip level 0. Level 0 is just no autonomy at all. Level 1 autonomy, I'm going to base all of these on aerial autonomy, just so we have really concrete examples here. And so in level 1 autonomy, the system is providing stable vertical positioning. So you still have a pilot that's flying the drone, flying the system, but they don't need to be super high skilled, because if they let go of the joystick for a second, the drone is going to maintain its altitude. So at this level, there's no ability to obstacle avoid or obstacle detect, but there is the ability to stay in the air without a pilot directly controlling the drone. Next, we have level 2, which is often called partial autonomy. So a pilot is still flying the system, but they can be a lot less skilled because the vehicle is able to hover in place on its own. So it might be able to sense an obstacle, but the only action would be a response to warn the pilot, not actually any like maneuvers or anything like that. And note that while level 1 can stay in the air, it doesn't maintain horizontal positioning. So it could drift into objects and crash, whereas level 2 stays in place. Level 3 is called conditional autonomy, and that's now we're getting to the point where a human is not piloting the system, but is often called an operator. They don't generally need to hold a remote control, and the vehicle might be able to sense and avoid simple obstacles. So a lot of systems that we see on the market, especially for outdoor operations, are at this level. The most common use is where operators set waypoints and the drones use GPS to determine where they are and navigate to those waypoints. It's often the responsibility of the operator to make sure there aren't major obstacles in the way. There's some simple obstacle avoidance that these systems have, but they're mainly waypoint to waypoint navigation based on GPS. Next, we have level 4 autonomy, which is called high autonomy. It's the first level at which an operator is not required to be involved in the flight. So the systems on board have SLAM capabilities. They're using real-time mapping to plan trajectories around obstacles, to navigate complex environments. These systems might also have additional capabilities, such as the ability to explore a specific volume, where the robot is making decisions about where to go. It's not just being told, go to this waypoint, but it's saying explore this space, and it's defining its own waypoints. It also can be told to collect complete visual coverage of an object, and it can again translate that into those local planning trajectories instead of a human defining those. And now level 4 is broken down here into smaller increments because there's often meaningful improvements that impact customers and use cases before a system fully reaches level 5. So at level 4B, the system is capable of semantically identifying obstacles and making decisions accordingly. So for example, a robot might behave differently around a human or a tree because it's able to classify the obstacles it's observing, or in the case shown to the left here, being able to identify dust, because to certain sensors, dust just looks like another obstacle in the space, but being able to classify it as dust and reason about it lets robots fly through dust while also avoiding a very thin wire, for example. And so that classification of the environment and things in the environment inform the decisions that that robot is making. And so at Exyn, we build autonomy, and this is the level that we're at. The Exyn Nexus is at level 4B autonomy. You then have level 4C. It's the most advanced category within level 4. The main advancement here is that an operator is no longer specifying goals in terms of anything geometric or location based, but rather something in plain language. So an operator saying something like scan the house at this address, and the rest of the mission execution is happening by the robot itself. Note that this level is being investigated at academia at this time, but to my knowledge, there's not really anything that exists commercially or like robustly in the market today. But seeing where kind of academia is researching and whatnot, this is maybe something we expect to come in the future. And then there's level 5, which is full autonomy. If you talk to roboticists, this is often the goal that roboticists are thinking about. But in reality, there's a lot of things, and it's kind of pretty far off. These are systems that would be able to fly in any environment, any environmental conditions, be able to reason about tasks as well as a human might. They'd have reliability that is more reliable than a human pilot. And so there are a lot of things that would have to happen to get systems to this point. So these don't really exist in academia or commercially yet. So with that overview of autonomy, we're going to move to a quick poll question. So you should all see on your side a poll question about level of autonomy, specifically what level of autonomy is GPS-based waypoint navigation with obstacle avoidance. Alrighty, we got most voted was level 4A. So to take half a step back and clarify that, GPS-based waypoint navigation with obstacle avoidance is actually level 3. So at level 3, operators are defining those waypoints, and there's GPS so that the robot knows where it is based on that GPS. It requires connectivity to GPS or some other kind of localization source. There is some simple obstacle avoidance, but kind of the human is defining those waypoints and GPS is defining the localization. In order to be at a level 4 or level 4A, the system has to be able to reason about its mission and kind of define its mission by itself. So instead of just waypoint-based navigation, there's the capability to define its own waypoints, and it doesn't rely on things like GPS or connectivity to the world, cellular connectivity or the like, to give it positioning. So it really requires something on board so it can stand alone and act in the world without needing external connectivity and the like. Great, thank you all for filling out that poll so I can make sure that we're all understanding there's a lot, autonomy is very new, and there are a lot of different nuances, which is why it's good to understand how these different technologies work, what their limitations are. Later in this talk, you'll also get a framework to think about not just when to use autonomous technologies, when to use SLAM technologies, when to use traditional technologies, but also how to think about and what questions to be asking when you're thinking about the type of autonomy to use. So that when you see something on the market, you're like, oh, it says it's autonomous, you can actually dig deeper into like, what are its actual capabilities? What level of autonomy is it? So next, I want to talk a bit about speed and accuracy. And so we talked about the technology. I want to talk about these as metrics or aspects that are going to be traded off so that we're all on the same page about the impacts these things have to end users, to customers, to surveyors, projects, and the like. So the technology was kind of on the what tech exists, and then this is on like what are the impacts on the application side of the world. So first and foremost is speed. Different technologies take different amounts of time, both in terms of total amount of time to get the data you need, as well as how much human involvement is involved in using that technology. And each of those impact speed in different ways. So for example, reducing disruptions is one of the really important reasons why speed matters. So oftentimes surveying requires site shutdowns, partial site shutdowns. If you are surveying a bridge, for example, traffic might have to be shut down, and that can be very disruptive. When it comes to autonomous inspections, this is something that can reduce disruptions because these can happen overnight if you're doing routine autonomous inspection. So you can imagine leaving a drone or a ground robot or something on site, and then when things are shut down, when people are away for the night, that's when scanning can happen to help reduce these disruptions. With all of these, there is a lot of things in the surveyor's toolkit, and so one of the ways I think about speed is what is, given certain constraints like accuracy or type of information that needs to be gathered, whether it is just LiDAR data or if it is ground control points, visual data, imagery, whatever it might be, what is the fastest tool that fulfills those constraints or those requirements. The second reason that speed matters is safety, which safety matters by itself, but speed can impact safety a lot. So surveying still has a lot of risk. Dangerous environments, whether it is construction, mining, transportation, oil and gas, and just being in those environments, especially when surveying, depending on what types of information is needed from the surveying, it involves inherent risk. And so if you can get that data faster, surveyors don't need to be in those environments for as long, and therefore reduce the risk that those environments present. The last thing from the speed front is cost efficiency. A lot of these industries right now are facing staffing and workforce challenges, as well as increasing demand, especially in the data capture world. And so there's a need for increased productivity. And so there's a need for capturing data faster, and there's also, jobs that are lump sum jobs where spending any extra time is added cost without added income. And so by being able to capture data faster, to capture more data with smaller crews, that is beneficial from a cost efficiency perspective. One of the things that is also very, very important is catching rework. So one of the things that scanning and monitoring progress by doing more frequent scanning, which is possible with faster scanning is catching rework. Rework is a very expensive problem, especially in the construction space. It's estimated to be billions to trillions of dollars annually due to the cost of rework. And I'm sure anyone who has had a project that involved a lot of rework, it can be a very painful process, and rework errors kind of propagate down the line to cause more problems. In addition to speed, accuracy is obviously very important, and I'm sure any of you who use any of these kinds of technologies care about accuracy, or have end users or people that you are providing this data for who care about accuracy. A few of the reasons that it matters is capturing the full picture of the world. So inaccuracies or occlusions impact decisions that are made on the business side. Making sure data is up to date. When data goes stale, that is one of the things that can lead to rework, or lead to decisions being made with inaccurate information, especially in fast-moving projects. Projects these days are only moving faster, gaining complexity, and so having up-to-date data is important. And then information that is aligned to reality. And so this is making sure that all of your data is true with respect to the world. And so on the accuracy front, I like to think about having all of the information spatially, having that information up to date temporally, and then having that aligned to reality, kind of like geographically. So we're going to go to another poll question here. Which of the following is most important to you? So this is one I'm just kind of like curious from the audience point of view. All of these things are important, but I'm curious, what you all would put at the top of the list in terms of either biggest pain point for you or things that are most important to you, whether that is minimizing site disruption, updating stale data, or catching rework earlier. All right, the most voted was minimizing site disruption. That's very interesting. It's great to hear. And yeah, one of the things that is really interesting with SLAM technology is both the speed of capture and the ability to move around, and the ability to kind of like filter out some things that are in the environment that are moving. All of those things enable lower site disruption. And one of the things that I think is coming, and that we at Exyn are building toward for the future, is the ability for autonomous robots to do autonomous surveying and data capture. And one of the reasons for that is to minimize site disruption. The biggest space for this is routine inspections, where you can leave a robot on site and do, every night when people are off site. And so you're gaining that very valuable data overnight. And so in the morning you have updated data without having any site disruption, since it happens while the site is inactive. Great, so now we will move to an actual decision framework. So I want to talk through TLS scanners versus SLAM scanners, and how you think about where each of them fits in, then how to think about where autonomy fits in, as well as how to evaluate different autonomy technologies, since there's a lot of companies out there and a lot of technologies that say they are autonomous, but as we saw earlier, there's a lot of different, there's a lot of nuance to what autonomy means. So I'm going to give you guys the tools you need to evaluate autonomy solutions, understand the differences between them, what their actual capabilities are, and what they can do for you. So there's a few disruptions that we've started to see in the LiDAR-based SLAM space, disrupting some of the traditional scanning methods. So two examples that I wanted to give here were traditional mining scanners that, one of the common ones is a scanner on a pole where they stick it into a newly blasted space because humans can't go in there. There's risk of collapse, there's human danger. These often have a lot of occlusions because you have a single scanning point, and if it's blocked by anything, you can't see that full area that has been blasted. It's obviously having operators and humans that close to these areas is dangerous, and it's also labor intensive. It usually requires multiple people because it's on a giant pole. It requires manual labor to get it in there, as opposed to, for example, using the Exyn Nexus integrated on a drone where it is doing autonomous exploration. Users can be further away from those blasted areas, send a robot in for it to explore on its own, fully map that place, and come back with that full data. Similarly, we've seen disruption on the tripod scanner space, where these tripod scanners are stationary, outdoors, GPS required, not as mobile, and can take a lot of time if you're scanning complex areas, as opposed to the Exyn Nexus in a handheld mode or a backpack mode, where you can walk the space, get into every part of that complex space to capture all of the data that you need, and to do that in a very short amount of time without the need for GPS or the like. And so as we think about these kinds of disruptions and whatnot, I really think about them on two dimensions, that is accuracy and frequency. You might be thinking, why are we not talking about speed here? We were talking about speed earlier. Speed is always beneficial. If you can get the same accuracy but faster, why not? But it is especially impactful when scanning has to happen often. And so that's why I break it into frequency and accuracy, and not speed and accuracy. So I want you all to think about some of the applications that you are involved in, how you use scanners. It could be some examples here which are low accuracy applications, whether that's site documentation, inventory, just imagery or pre-construction documentation, or maybe you have some of more higher accuracy needs that are QA type stuff, survey control, ScantoBIM, routine inspection, depending on what you're inspecting, requires different levels of accuracy. And I want you to think about how much accuracy you actually need, and think about how would your job change if you increased or decreased the frequency. So if you take one of the examples on like on this diagram, and you moved it up or down, if you did that work more often or less often, what would the impact of that be? And so thinking through these different applications, I want to show where different technologies fall in this space. And so the first one is traditional laser scanners, total stations, those kinds of technologies. A lot of that technology lives on the right side of this, high accuracy scanning needs. And these are the ones that I expect many of you are using traditional TLS for. When we think about SLAM scanning, we think about the left side here. SLAM scanning is on the lower accuracy side, but one of the really interesting things, even in just the last half decade, is we have seen SLAM technology expanding towards that higher accuracy side because of improvements in the fundamental technology, improvements in accuracy, improvements in sensors, improvements in software methods. And one of the things that I think is also really interesting to think about is as speed increases and as we can capture data quicker with SLAM scanners, that lets you increase frequency. And so we can actually move things up on this chart as we can scan them faster. That enables us to scan them more frequently, which again can help us tackle things like catching rework earlier, catching needed maintenance earlier, so it doesn't then lead to breakdowns if it comes to, asset inventory and the like. And the last thing is thinking about autonomous robot opportunities. And so really I think about this in the high frequency realm. And so whenever things need to happen often and a lot and take a lot of human labor, that's when I think autonomous robots have the best opportunity to provide value, because they can do that on repeat overnight, those kinds of things that we talked about, where they're on site permanently and they are capturing data frequently while the site is, while people are off site for overnight or whatever it might be. I also now want to talk about thinking through autonomy needs. So we saw, where do these different technologies fit in when it comes to speed, frequency, accuracy? Where does traditional laser scanners fit in versus SLAM scanners and autonomy? But again, I want to break down, when you think about autonomy and you see things on the market, what are the questions you should be asking? And so one of the things as a place to start is what your data needs are. So if you only need visual data versus LiDAR data, depending on your accuracy needs, what you're trying to see or do, if you're doing inspection, LiDAR can sometimes fit that need, sometimes visual, depending on what you're inspecting. You might need high resolution visual data versus lower resolution, and then also the direction of capture. If you just need to be overhead or below things, what your occlusions could be when you think about autonomous robots. That informs whether you're going to be using a ground robot or an aerial robot or a mix of both. You then have to think about operating conditions. There are some robots that can that require illumination, a lit up room, and can't fly in the dark. There are robots that can't fly through dust or fog. Robots have different battery capacities, flight durations, flight speeds, day versus night operations. So you have to think about those operating conditions and ask about, both for yourself, what do I need in order to capture the data I need? And then asking to technology providers, what are the capabilities of your robots with respect to these operating conditions? Next, you can ask more about the operating capabilities, both of your applications and your business. So a big one is whether or not you have pilots. For some technology that is low autonomy, you still need pilots. They need training, they need certification. You might need remote operators. If you don't have those, or if you're thinking about adding them to your team, that's a lot of work, that's a lot of an investment. And so those are times when you maybe consider higher levels of autonomy. Additionally, you have to think about connectivity, because remote operators require remote control connectivity or wireless connectivity, cellular connectivity. Like we talked about earlier, lower levels of autonomy often require GPS, and there are a lot of GPS deficiencies if you are inside buildings, under canopies of trees, or in urban canyons. So you have to think through all of those for your applications, and then again, ask about them to see whether the technologies of autonomous robots and which technologies on the market fit your needs. And then the last one is the technological capabilities. And so in addition to needing GPS connectivity, lower levels of autonomy often need a prior map, or they need certain information about the world. They need things in the world to tell the robot where it is in the world, those types of things. They sometimes can or can't handle large or small obstacles, moving obstacles, and the like. To give you an example, the technology we create, the autonomy we create, as I told you, is a high level 4B autonomy. The robot needs no prior map information, no connectivity, no GPS or RC, no information about the world whatsoever. So you can think about it being fully self-contained. So it can be given a high-level mission that is still defined by a human. Once that mission is given to the robot is on its own and can handle itself in complex, challenging environments without any kind of prior information or connectivity. So it's very much so a standalone autonomy, which you only often find at these very high levels of autonomy. So with that, we'll move to another poll question, asking you guys which of the following is the best application for autonomous scanning. Great. So most voted was for progress monitoring and routine inspection, which is correct. So glad you all have a good understanding of autonomous robotic scanning and kind of where it fits in. One of the things to note is a lot of these technologies, such as the Nexus that we make and the autonomy on board, can be used in a lot of different applications. In this case, like high accuracy quality assurance is not a space that SLAM scanning usually is used for. You're still using those, traditional high accuracy scanners and traditional methods, but things like project site documentation, that's one where, sometimes can be used if you have autonomous robots or handheld SLAM scanners, you can use it for that. But the autonomy and autonomous scanning is the biggest unlock for progress monitoring and routine inspection. So the last section here that I want to talk through is some real world case studies. So you can see, how is this being used? What kind of impact are we actually talking about here? How much of an impact? And you might be asking yourself, how do you, how do you know about this? Where has our experience in this space been? So Exyn sits at the intersection of high quality 3D mapping and high level autonomy. And we've been working at this for over a decade, both on building capable and flexible mobile mapping and autonomous navigation products, but also spending a lot of time in the field watching and listening to users so we understand the data that our systems capture and how our end users use that data. So our current flagship product is the Exyn Nexus. It is a fully modular 3D mapping system. And when I say modular, it's because it can be used in handheld mode. So what's shown here is the handheld version that has a quick release handle on it. But we also have mounts so that this can be mounted on a backpack mount. So if you're, doing longer scans and whatnot, you can mount it on a backpack and just walk around with it or capture data while you're doing other work. It can be mounted on vehicles, and this same device can be unhooked and put onto a drone. So we integrate with a bunch of different drones, ground robots and the like, and that's when you unlock the autonomy that is on board here. So a lot of our customers are using this both in autonomous mode as well as in this kind of handheld or backpack manual capture. And sometimes they're even using it, back to back is, one day you're using it on the drone, the next day, out in the field on a backpack, sometimes right after one another. They have quick releases, so you can easily send a robot off onto a mission, for example, to scan the outside of a building, and then with a single button, release it from the drone, hook it onto a backpack, walk it inside, and you're now able to very quickly get indoor and outdoor capture. And so when I talk about modular, that's kind of the powerhouse of the Exyn Nexus. So one example I want to give here is on the autonomous drone front. So this was an example with the US Army Corps, and they were doing 3D mapping of an urban environment. So you can think about bridge, tunnel, dam inspection type stuff. So in this example, they sent out a single autonomous flight, which took 4 minutes, which sounds like, oh, 4 minutes, what can you get in 4 minutes? But our robot flies at around 2 meters per second and can cover a good amount of space, even in 4 minutes. 4 to 5 minutes with all of our mining customers is actually kind of the median flight time that's needed for them to capture all of the data they need, because it can cover space pretty quickly. In comparison, traditional methods with a tripod system for this scan would have taken over 30 scans and an hour and a half to complete, instead of a 4-minute single autonomous flight. We can also look at an example that was not an autonomy example, but using the Exyn Nexus in a handheld mode. And so this was a complex historical site that they were scanning, and the building was occupied, so disruption and site disruption was a very important project requirement. There were high accuracy requirements, and so traditional methods were used to establish control outside. So using, for example, a total station to have targets at entry and exit points to the building. One of the cool things with the Nexus is it can incorporate both ground control as well as GPS. So if you're starting outside and getting that global reference frame and then moving inside, you can use ground control to get high accuracy, and you can use GPS to anchor in that global reference frame, and it naturally pulls that data in and uses them to create as accurate of a map as possible, balancing the uncertainty it sees in GPS. For example, when it's indoors, it's relying on SLAM, and when it's outdoor, it's using the SLAM accuracy as well as the GPS accuracy in that case. And so in this case, they were able to do what was expected to be a 5-day survey in half a day, and reducing scans times by 20x. And so with this example in the previous one on the autonomy case, you can see kind of the speed that you get with that, and kind of what that unlocks for end users, whether that's on the minimized site disruption or just getting data faster. And so with that, I want to thank you all. I think we maybe have questions.
We'll wait for some more time if there are any questions that the audience would like to bring up. Uh, no worries. So if there are any questions that you think that you might come up with at at a later stage, you can share it with us. We'll ensure that it is shared with Matthew for follow up. Right. From there, I believe this concludes our today's session. Matthew, thank you once again for an outstanding presentation and for sharing your expertise with us today. And to everyone who joined us today, thank you for spending your time with us. On behalf of everyone at Virtual Building Studio, we truly appreciate your participation and engagement. A recording, a recording of today's webinar will be sent to all of the registrants shortly. So please feel free to share it with your colleagues who may benefit from the discussion. As reality capture technologies continue to evolve from terrestrial laser scanning to SLAM-based mobile mapping and autonomous robotics, the ability to make the informed decision before field deployment will become increasingly important for delivering projects faster, more safely, and with greater confidence. We hope today's session has provided practical insights that you can apply on your very next project. Thank you once again for joining us. We look forward to welcoming you to another virtual building studio webinar in the near future. Until then, stay curious, keep learning, and have a wonderful day. Goodbye, everyone. Thank you.